Okay, this video is for AP Calculus, and we're going to talk now in this unit about applications where we can use the integral, either the indefinite integral or the definite integral. And this first one we're going to talk about is computing the area between two function curves, or beneath a function curve. So we'll build off the definition of the definite integral that we've already seen. One of the definitions that we have for this integral symbol nicely illustrates this idea that integrals are really summing machines, right? The reason that we use this symbol for an integral is because it's kind of an elongated S that stands for summation, right? Which means you're summing something up, right? So if you do an integral of f of x dot dx, this is a little tiny sliver of some quantity, right? Maybe a little tiny change in the width, delta x. And then this h can be something. When we did Riemann sums, we made that h the height of a rectangle. So that was a little height and a little tiny width. And that means together, this formed an area, right? The area of one of these little sliver of rectangles, right? I have to imagine that this delta x is really, really small. This dx is an infinitely small delta x. But then if we sum, that's what this integral symbol says, if we sum up all these areas, we get the overall area under the curve, right? So this nicely illustrates that integrals are summing machines, right? But what that means is that this can be anything as long as it's being multiplied by a little infinitely small quantity over here, right? So you can sum other things. You don't have to have areas out here. There's other things that we're going to explore. But we'll start with area. We'll just add on a little twist to what we already know, that we can take the integral where we have a height here. This function establishes the height from the x-axis up to the function curve, and then times the width, delta dx, delta x, but infinitely small. And then we find the area by using the integral. So you can think of it as the form for a Riemann sum, a height for the ith rectangle times, we should say width here, actually, that's a typo. That width becomes the delta x, the height becomes the function height at that selected x. When we do Riemann sums, it's either mid or left or right, and then we sum n of those rectangles. If we take an infinite number of rectangles, let n approach infinity, then this whole structure here becomes the integral symbol, a smooth summation. The integrand becomes the height, and the delta x becomes dx. This is the differential, dx, which is an infinitely small little change in the x direction. Okay, so just reiterating some terminology that we're already familiar with, hopefully. So we can find an area by taking something that represents a height and a little tiny change in the width. We label that dw, multiplying those things together form an area, and so the summation produces an area. All right, so what if we wanted to find the area between two function curves? So we have a curve f of x that has more positive values and a g of x which has less positive values, and we wanted to find this yellow area in between. Well, what we can do is you can just first find the area underneath the top rectangle like this. Right, so you could write it this way. That would be an area with f of x as the height, integrating from a to b. Right, and then you could subtract out the area that is below the g function curve. If we subtracted that area out also from a to b with g as the function curve, what would be left would be the difference, right? So this difference would be the first integral minus the second, and that would be the area between the two curves. Right, so you can think of it that way, and you can actually even do two separate integrals. In fact, in later sections, we're going to just generally do two different integrals. When we have this case where we have a more positive function curve and a less positive function curve, we'll find something with the more positive value and we'll subtract out the middle to get what's in between the two. Right, so if you want to do it this way, that's absolutely fine. You can simplify that into a single integral that is just one integral from a to b of, but then you have to say you're taking the f of x distance minus the g of x distance, right? And you could think of that as a height if you say, okay, wherever f of x is minus g of x, that difference there is what we can label the height, this h. We've got to use a little h here, right? And that has to be the f of x, which has to be the, you could call it the top function, and this one the bottom function. Sometimes I'll use the words floor and ceiling when or floor for the lower one, ceiling and floor um, when I teach this in class. But what we're really talking about is the more positive one here and the less positive one here. So whatever direction is up on that axis, this has to be the leftmost one. The reason being is this area should be a positive number, and so this number always has to be higher than this number. So you have to have the more positive number here on the left positive number. Okay, so some more terminologies, right? These values from A to B are the limits of integration. They are x values, so these numbers here, if this is x, those are values for x, and this is x equals a starting a and an ending, or starting x and an ending x. And what you want to think of it as is if you've got this one sliver of a rectangle, let's just highlight that in red here, right? You don't want to integrate any rectangles out of here, right? But you want to start integrating rectangles right here, where you get to x is a. And then you want to sum all the way until you get over here to x is b. And then once you get to x is b, then you want to stop. You don't want to include any rectangles out here. So this is the starting and ending values of x. And it's just good to think of it as taking that rectangle and sliding it in the x direction. Where do I want to start? And where do I want to end that? This is the a and this is the b, the values of the x variable. Okay, I know I'm taking a lot of time to talk about this basic idea here because it's really, really key to understanding things later when this is more complicated. Okay, so we're just going to do a few problems. The first one says to find the area enclosed by these two function curves. Now, the first thing we should always do is sketch the curve so we can see what's going on. And there's two ways to do that. If we're on a part of a test where we can use a calculator, we can use a calculator to graph, or if we're not, we're going to have to use intersections to graph by hand. So I'm going to show both ways because it's so critical to be able to sketch these things. Now, hopefully you're familiar with the idea of using your calculator's functions for graphing. But just to be clear, right, you would go to y equals and enter the two function curves. So y equals negative, make sure you use this, not the subtraction key, negative x plus 1 for one function, and then negative x squared plus 3x plus 1 for the other function. And then when I graph, I usually just do zoom 6, which is origin plus or minus 10. Usually that gives me what I want to see. There's the line, there's the curve. And then if you want to know where intersections occur, like for example, where is this intersection? You can go second, trace, and then select intersection. You position it in the vicinity of that intersection. You tell it, okay, that's the first function curve, enter, second function curve, enter, and then the guess is roughly there, and it'll position that it's at 4, negative 3. Right, so that's one way to get that it's this area right here that we're finding the area between the function curve. And if you're lucky enough to have this on the calculator portion of the AP exam, that's fine. But remember, half of the AP exam is no calculator, so we also have other techniques for finding things like graphing information. And so the other way to do this would be to graph by hand. So how can we graph this by hand? Well, what I would do is maybe think of this as a system. So if you say y equals negative x plus 1 and y equals negative x squared plus 3x plus 1, anytime I'm interested in the intersection, think of it as a system, because the intersection will be the xy pairs where everything in the system is true, or makes both equations true. So by substitution, I can substitute this in for this, and that gives me negative x plus 1 has to equal negative x squared plus 3x plus 1. I'm going to move everything to the left side. So I've got, let's see, that's a positive x squared here. I've got minus x. When I bring 3 more over there, that would be minus 4x's. And then I have a 1 that I subtract from both sides. That's going to give me 0 then, equals 0. And then hopefully you'll be able to, if this is on the non-calculator part of the test, you'll be able to solve this by factoring and get that this happens when x is 0 and when x is 4. So those are two possible locations where we have an intersection. To find the matching y, we can substitute into whichever of these seems easier. Y is negative x plus 1, so negative 0 plus 1 would be 1. So that's the point. X is 0, y is 1. And then if I plug a 4 in here, that's negative 4 plus 1, which would be negative 3. So when x is 4, y is negative 3. So that gives me some pretty good information. I can now sketch that. Let me just make a sketch over here. Okay, here's x, y. Now I'm just going to locate those intersections. So let's put some tick marks on here. We have to go out to 4. 1, 2, 3, 4. So let's go 4 in all directions. It's the biggest number on here. 1, 2, 3, 4. So I want to go to 4, negative 3. That's one intersection at 4, negative 3. And the other one is at 0, 1, which is here. Right, so locate the intersections and then just look at the function graphs. Right, one of these is a line. So there has to be a line that goes through those 2 points. So I'm just going to sketch a line through those 2 points. And then the other one is a y equals x squared curve with a negative, so it's got this general shape, and it has to go through those 2 points. So just with that information, I can just sketch it like that. This perfect. But this is what my goal is, to be able to see the general shape of what's happening. Okay, now that I know the general shape, I can go back and say, what area are they talking about? The area enclosed would be this area. Right? And that means we're going to put a rectangle on there. I'm just going to go somewhere in the middle of this and just draw a rectangle. Okay. So the first thing is, I want to just say this little tiny incremental width here, this infinitely small width, is in opening horizontally. So that's in the x direction. So that's dx, a little tiny change. And then I'm going to label this h for the height. Right. So since I'm finding an area, now I'm going to make an integral that matches this. This area is an integral. Well, in general, it's an integral from a to b of the height times a little incremental width. And so now I know that this incremental width is in the x direction. And for this height, I'm going to imagine that we have, let's see, there's a y on the top of this, and there's a y on the bottom of this. The reason I'm saying y's is because this h is moving in the y direction, so I have to have a y where this starts and a y where this ends. Right? You can talk about it like a floor and a ceiling, or a top and a bottom. Right? But for this to be positive, we have to take the more positive value and then the more negative value. So the more positive value here is this function right here, and that function is the curve. So that means, looks like I'm going to need to write this a little more room here. It's going to be the top function, which is the curve, so that is negative x squared plus 3x plus 1, and then minus the bottom curve, right, which is the negative x plus 1. Right, so this is like the top f minus the bottom f. And that's giving me the height. And then times dx. And then, since this is an x, I have to start at a smaller x and end at a larger x. So the smallest x is, if you imagine now that you were sliding these rectangles, you would include all these rectangles to fill up this space. So this is going to start when x is 0, and it's going to end when we get to x is 4. So the limits of integration are 0 and 4. Right, so that's the setup. Right? The most difficult part of that is the setup itself. Now, how do we evaluate it? It does say to find the area, so depends. If a problem says set up the integral to find an area but do not evaluate, then this answer alone is sufficient. If it says to find the area, then you have to report an area, right? And there's 2 ways to do that. If you have a calculator, you can use the math9 function. We could do that. So let's show that real quickly. Now that I have my calculator with the functions already in there, because I graphed it, which one did I put where? I put the quadratic as the y2. So I'm just going to say math 9, an integral from 0, and then go up here to 4. And then rather than typing that 8 again, I'm going to say if I go to variables, y variables, and then these are function variables, y2 is the curve, minus variables, function variables, y1 is the line, and then I use variable key to indicate the variable, and then that gives me the answer is 10.666. Now, if you are reporting this answer in decimal, then it has to be accurate to 3 numbers after the decimal. So you don't have to say that you did math 9. Just show the integral and then say 10.667 is the answer. Okay. Now, what if we didn't have a calculator? If we didn't have a calculator, then we would have to integrate this by hand. So let me write the integral again. I'm going to get rid of the parentheses here. So I've got an integral from 0 to 4, negative x squared plus 3x plus 1 minus minus is plus 1x minus 1. Okay. And actually, before we start, I can do a little simplification. The plus and the minus 1 cancel, and these combine to be 4x. So let's make this as simple as possible before we start. And that is going to be, now we need to take the antiderivative by hand and use the fundamental theorem. So this would be negative 1/3 x cubed plus 2x squared integrated from 0 to 4. And then we could take our two copies, 1/3 something cubed plus 2 times something squared minus another copy, negative 1/3 something cubed plus 2 times something squared. And then we'll plug in the 4 here and the 0 here. Okay. If you integrate by hand, don't waste any time simplifying, because if you do simplify, then they have to take points off and they will count this as correct. So this number, if you did plug it carefully in the calculator, should be the same thing we got as well. Then finally, if this was a word problem that gave units and these dimensions say were in inches, then you would have to say that this is square inches because it's an area. But you shouldn't make up units, like don't put u squared there, just the number alone if there's no units provided. All right, so that is an area enclosed example, and hopefully that felt pretty comfortable. Okay, we've only got a few examples here because it'll take a little bit of time. Let's try this one. Now this time we've got curves that are solved for their x variable. Find the area enclosed. I'm going to jump straight to doing this by hand rather than the calculator. So let's do that. Let's graph. We'll do the same thing we did before, where we think of this as an intersection. So let's do this here. X equals negative y, and also x equals negative y squared plus 2y as a system means that negative y would equal negative y squared plus 2y, which means y squared, if I get everything on the left, and then if I subtract 2 more, is minus 3y equals 0. Y times y minus 3 equals 0. So y would be 0, or y is positive 3. And if y is 0, x is negative of that, so x would be 0. And here the x would be the negative of the 3. So the two intersection points are x is 0, y is 0. And here x is negative 3, y is 3. Be careful, we solve for the y, so that's the second part. All right, so if I'm graphing this, I'm thinking, okay, we have x, y. There's an intersection at 0, 0 at the origin. Looks like we have 3, so we just put some tick marks in here to get at least out to 3. So if I go x is negative 3, y is positive 3, that's this point. So we have the point 0, 0, and the point negative 3 for x, 3 for y. One of these is a line, so we have a line. And the other one is an upside down parabola, right? But this time the x and the y are swapped. So instead of this going this way, it's going to be opening in the downward x direction. So it's going to be this kind of shape. So if I imagine a shape like that, right, that would look maybe like this. And so sorry, that's not a very good drawing, but yeah, a parabola. And that means this is the area we're talking about in here. Okay, so let's try to cover this with a rectangle. Now, the first thing you might think of would be to go ahead and do what we usually do and put the rectangle up and down. Let's try that. If we decided to do that, that means that this width would be in the x direction. And let's see, this height here would be where we'd have a y on the top and we'd have a y on the bottom. So let's figure out what those things are. The top function is this square, which means we somehow have to solve this for y. Okay, well, let's do that. Let's see. If I, oh man, this would be really complicated. It could be done. What I could do is this. Let me swap sides here. Negative y squared plus 2y equals x. I'm going to negate everything. So y squared minus 2y is negative x. This is actually not the way to solve it, but I want to show you why, to show you how bad this would be to do this with your rectangle up and down. If you're screaming at the screen right now and going, why not put the rectangle horizontally? You're exactly right. That's what we're going to do. But I just want to show you how bad it would be if we didn't have to do that. Okay, so don't copy this because this would not be the way to do it. But if you wanted to do this, you could complete the square on this side, which is an algebra procedure that we learned back in, reviewed again back in our integration techniques. This would be y minus 1 squared, but then we would have to add a 1 here and balance it with a 1 here, and get negative x plus 1. Right? And then you can take the square root of both sides. Y minus 1 is plus or minus the square root of negative x plus 1, and then add 1. So this is 1 plus or minus the square root of negative x plus 1. Wow. All right, and we're talking about, let's see, 1 plus. So if I'm on this part of the curve, okay, this is really crazy. Right? So from this part of the curve up here, this y is going to be the positive 1 plus the square root of negative y plus 1. But for this part of the curve down here, it would be the y is 1 minus the square root of negative x plus 1. Wow, that is crazy. But, yep, we're just going to keep going here. Okay, the other curve is not as bad to solve for the other variable. If x is equal to negative y, then that means y is equal to negative x. So that's pretty straightforward. This y would be equal to the negative of x. Okay, so now we have y in terms of x. But what that does mean is that we're actually, we're going to have to split this because, right, if you look at, there's another color to highlight this. If you look at here, this is the bottom y for this portion, right? But then when we're on the other side of the y-axis, it's the same curve for the top and the bottom. That means we're going to have to split this into two separate integrals, one to do the integral on the right, the area on the left, and one to do the area on the right. So continuing, we could do it this way, but I'll show you the integral setup. For the left, the area in this first part here would be an integral from x is negative 3 to x is 0. Right? The top function would be this, so that is 1 plus the square root of negative x plus 1. The bottom function would be the line, y equals negative x. And we would integrate that in the x direction. Right? That would cover this area. But then we'd have to do another integral that goes from here to here. And then I got to figure out, well, where is this? How far does this go over? Right? So maybe what we can do is in this location, if we remember our conic sections, we can see that the vertex of this is at 1, 1, because this is equivalent to y minus 1 squared equals negative x minus 1. So the vertex of this parabola is at 1, 1. So this point is actually 1, 1. And we would then integrate from x is 0 to x is 1. We would use this portion on the top. So this would have to be 1 plus the square root of negative x plus 1 is the top function. And then that same function, but the minus case on the bottom. Negative x plus 1 there, dx. Okay, so this will work and give you the correct answer, but man, is that a lot of work. All right, so thankfully, there's an easier way to go. So hopefully you've already anticipated it, and it is that we're not going to put our rectangle up and down. We're going to put our rectangle left and right. That's going to solve a lot of problems and make this much easier. So let me go back to here, and we'll sketch it again. But this time, we'll solve it with the rectangle in the other direction. Okay, we'll make the sketch. Here's the sketch. We said that this would intersect at 0, 0, and also at negative 3, positive 3. Okay, one of these is a line, and the other one is a parabola like this. And we're finding this area in here. Okay, so the change we're going to make is, and pretty much whenever these are solved already for x, it's going to make more sense to put the rectangle in the other direction. And so if I put my rectangle this way, now that means this width is in the y direction, right? So whenever I do my area is a height times a little change in width, that is now going to be in the y direction. So this will be a y-type integral. But that means that on the ends here, we've got two ends. We've got an upper end, but now this isn't a top x, and this is a bottom x. So the top x is going to be the curve, so it's already solved for x. It's negative y squared plus 2y. And the bottom x is just negative y, so we didn't have to change these to the other form, which is nice. And that means that our area is going to be an integral of a height, and that height, the top x, is negative y squared plus 2y. The bottom height is negative y. And then, let's see, we're integrating from, this is dy, so this has to be a y value. So if you imagine you're sliding this rectangle up and down, you start here at y is 0, and you end when you get to y is 3. So this is what we're integrating, right? And you could do this by hand, or you could do math 9, but the result ends up being 9 halves or 4.5. Okay. All right. So whenever you see x equals, most likely the rectangle is going to be the other direction, right? But the real thing is, just analyzing this situation here, right? If we had, you can try placing your rectangle this way, but realizing that means that there's one set of floor and ceiling here, and we have to switch to a different set of floor and ceiling here. That would mean that vertical rectangle is going to require that we have multiple integrals to cover that. As soon as I detect that, if possible, I would try something else, right? On the other hand, if you bring that point home, if you have that same function curve, like this, okay, then if you decide to put your rectangle this way, then that means for the entire area, we have one top x function and one bottom x function. So only a single integral required. That's why this is the superior orientation. Okay. So you can do what we call integrating with respect to x, or you can do what we call integrating with respect to y, using the y variable as the variable of integration, depending upon which has fewer regions. Now, once you decide to make that decision, once you've set this, then it means everything in here, these functions can only contain x's, and these values are x values. If you decide that you're doing a horizontal type rectangle, this is a y. This only contains y's, only y's, and these are y values. So the entire integral is one variable or the other. You can't have mixtures of variables. Okay, one last example. And if you want, you can try doing this either with a calculator for graphing or by hand, and then unpause the video. This is the last example for this video here. All right, I'm going to focus on non-calculator methods here, but of course you could graph with a calculator to find this. I think this will work. If I treat this as a system, this is like y is the cube root of x minus 1, y is x minus 1 as a system. If I set those equal, I would have, let's see, x minus 1 equals the cube root of x minus 1, which means I could cube both sides. Now then, I think maybe what I do is I'd multiply this out. So there's 3 of these. Let's do FOIL here. That's going to be x squared minus 2x's plus 1. And then when I multiply this in, everything in here times an extra x. So x cubed minus 2x squared plus x, and then everything times a negative 1. So negative x squared plus 2x minus 1. And then I can gather all the terms together. So let's see, on this side we have an x cubed. We have a negative 2x squared minus another one that's negative 3x squared. We have an x and a 2x, that's 3x, but I'll subtract this x over, it's back to 2x. And I've got a negative 1 on both sides that would cancel out. Okay, and then this I could take an x out, and that would give me x squared minus 3x plus 2, which I think I can factor that into, what is that, x, is that factored? 2 and, yeah, x minus 1, x minus 2, right? Because that would add to negative 3 and multiply negative. Yep. So there's 3 intersections. X equals 0, x equals 1, x equals 2. All right, let's go ahead and find the match of y's. Y is x minus 1. So y would be negative 1 here, y would be 0 there, and y would be 1 there. So the points of intersection are 0, negative 1, 1, 0, and 1, 2. Okay, let's make a sketch. Oh, man. Okay. So looks like everything's maybe only up to 2. Let's just do 2. 1, 2, 1, 2, something like that. Okay, 0, negative 1 is here. 1, 0, 1, 0 is here. And 1, 2? No, 2, 1. 2, 1. Oh, sorry, I got back to up. This is 2, 1. And this is, get that right. This is, let's see, 0. That's even wrong. Let me just redo that whole thing. Okay, we'll start the graph over again. Okay, so for the graph, zero, negative 1 would be here. 1, 0 would be there. And 2, 1 would be here. There we go. Okay, one of these is a line. And the other one is a cubic function. Well, it's a cube root function. So like y equals x cubed would look like this, right? So x equals y cubed, which is what we have here, would be that on the other side. Might have to try something here. So it's not super obvious to me which way to graph it. So what I would do is I would pick another point, a couple of points in here, and just kind of plug them in and see what's going on. So let's say that I plugged in the fraction a half. So what is f of a half? So that is the cube root of a half minus 1, right? And a half minus 1 is the cube root of negative a half, right? Which is, you can take a cube root of a negative. So it's going to be 1 over whatever the cube root of 2 is. So what number times itself 3 times is 2? It's definitely something under 2. And I might have to just resort to a calculator to graph here. So by hand, most likely something that's not this complicated, but I'm just going to jump to the chase here because we don't want to go too long. If you sketch it in, a half ends up being down here for the y, so that ends up looking like this. So the function looks like this if you graph it. And there's actually 2 regions to cover here that are enclosed. All right, so that gives me what I need to be able to, enough detail to analyze to find the data. So for the area, let's put a rectangle on here. Now, which way should we go? I would go with this version, rectangle upward, which means we're doing a dx type integral. And also for here. So the difference, though, is that the line is the top function in this part, and the curve is the top function for this part. So for this area, and do an integral with the line on the top. So that's going to be x minus 1 on the top minus the cube root of x minus 1 on the bottom, integrated over x, and that's going to go from x is 0 to x is 1. And then I will add a separate integral, go the rest of the way from x is 1 to x is 2, but this time the cube root will be on the top because it's the more positive value. So cube root of x minus 1 and then minus x minus 1. Right, so this is the integral that would set this up. If you integrate this either by hand or with Math 9, you end up getting that this is 1/2. Okay, so the setup is the more important part. However, we will ask you to finish. Usually in our class on this part of the test, we focus more on the setup, and we have used Math 9 calculator to get the decimal number. But sometimes on the AP test, they do ask you to integrate. So we don't want to, now that we've learned how to integrate, we don't want to lose that integration skill. So I want to continue to do at least some of the practice by hand. All right, that should be the last one for this video. Hopefully that gives you what you need to be able to try some homework.